Well, first, I'd like to thank the organizers. It's certainly an honor to be able to speak here today. So I'm going to talk about separating astrophysical sources from indirect dark matter signals. I should mention this is going to be a very gamma-ray focused talk. I'm not going to talk about neutrinos, but Doug already covered that topic very well in his talk right before lunch. I won't talk about charged particles either. Stefan covered that very well in his talk before lunch too. So I do want to mention, though, that Stefan presented a lot of very exciting results with gamma rays, and I do want to emphasize that this is a very exciting time. I don't want to sort of put a damper on this, because I'm going to talk about the challenges that we have in actually confirming a dark matter signal in gamma rays. So I'm not going to tell you about the nature of dark matter, which we've heard about over the past day and a half. I do want to point out a couple assumptions I'll be making in this talk. In particular, I'll assume that dark matter is a WIMP. So I need a GeV to TeV mass scale so that it makes indirect signals in the energy range of the instruments I'll be considering. I need it to pair annihilate or decay to produce something including photons. And I'll assume that it accounts for the measured dark matter density. So to begin, to give a big picture sense of what the challenge is, the challenge of finding these dark matter signals, I'll start with the gamma ray sky as observed by the Fermi lat. Stefan showed this map as well. So he pointed out some of the main features you'll see here. We have the galactic plane, which is this very bright emission in the center of the galaxy and along the plane. This is coming primarily from the interactions of cosmic rays with the interstellar gas. This ends up being a major foreground for us and can also produce confusing signals. We also have diffuse emission that extends to high latitudes, as well as the isotropic diffuse emission, and we have point sources. So to see what the issue is, we can compare this to an expected dark matter annihilation signal. This is gamma rays from annihilation just from structures in our own galaxy. This is one example for a particular model of the structure of our galaxy. And immediately you see that this does not look very much like the map we just looked at. So we know right off the bat that most of the photons that we are collecting are probably not coming from dark matter annihilation or decay. It gets a little bit harder when you actually convolve this map with the angular resolution of the Fermi lat above about 10 GeV. So this is what the sky might look like. It no longer looks like you can see so many crisp little subhalos, but instead it smooths out quite a bit. You'll see that the emission looks fairly isotropic on large scales. There are still some bright spots. These could be very interesting targets as well. And you can still see the galactic center very well. It's a very bright target. But again, going back to this map, it's clear there are also some important foregrounds to consider in front of that. So I think it's fair to say that the challenge of separating these dark matter signals from astrophysical sources is very akin to the classic problem of finding a needle in a haystack. But I would actually argue that it is a harder problem than that. So the reason is, so we're all physicists in this room, and if I asked you to go in to look at this haystack and find the needle that I know is in it, it might not be the most interesting question that you've ever tried to address. But we're all very clever. We'd come up with some interesting ideas on how to do it. For example, you might try to design some optimal filter. You'll take what you know about hay, and you'll take what you know about needles, and you think, well, maybe I can design something, some way that I can separate them out based on, I don't know, something about their size. Or this could be akin to something like using the energy spectrum of dark matter, and perhaps we know that to be different than the astrophysical sources, which would be the hay. You might even get more clever and try to use something like the Brazil nut effect to separate components. The problem with all of these approaches, though, is that you don't know how big the needle is. We don't know exactly what we're looking for in terms of the dark matter mass, or in some cases even how big the signal would be. So without knowing that information, it's a lot harder to come up with an optimal filter. We're going to have to try many different filters to do this. So next, we might actually say, OK, well, fine. Maybe I know that the needle has some property that is somehow different than hay. Maybe I'll try, and I'll use a magnet. I'll try to pull it out that way. And this would be taking advantage of a special property of the needle. The problem is you don't always know that it has that special property. What if the needle is plastic? Then your search method won't work. So now you're probably sitting there scratching your head thinking, well, what do I really know about hay? And what do I really know about needles? And you might look a little closer. And as you look closer and closer and sift through more and more data, you start to find things that might surprise you. Maybe you'll find things that aren't exactly hay, could even be dangerous, things that you might never have expected in the first place. And so in the end, you find several things, but maybe none of them are needles. And so what do you do with what you've got? So I'll summarize this as saying the challenge is to detect an uncertain and very likely subdominant signal in the presence of uncertain backgrounds. And this is true for most of the targets that we'll consider. Now, there is sort of a light at the end of the tunnel. I should point out that I'm not giving you just one haystack, but I'm giving you quite a lot of haystacks. And they'll have varying things in them other than hay. There'll be varying amounts of needles. So we can actually optimize our search strategies, and we can choose which ones are the best targets. So I'll summarize some things that might seem obvious, but I think it's worth saying them so we can keep them in mind. The best approach is going to depend on both the expected dark matter signal and on the target source or emission. So there is no one-size-fits-all approach, and certainly they all have different uncertainties. So it's important to both optimize and also compare your results from different experiments. And on that note, complementarity is really key to make the most of the data. We want to use information from other dark matter searches, both indirect and otherwise, but also I want to focus on how important it is to use studies of astrophysical sources to better constrain our dark matter models and to improve our search strategies. In particular, multi-wavelength and multi-messenger studies can help to leverage searches beyond a single experiment, and naturally they can help alleviate issues with systematics. And finally, we'll want to make sure we're making full use of complementary results to help efficiently direct future efforts. So in this talk, there's a few tools that I'm going to come back to. The first is spectral information. Naturally, we already have heard, we know that the dark matter signal may have some unique signatures in the energy spectrum. Spatial information, as I've already shown you, the spatial distribution of the dark matter signal does not match up with the astrophysical sources. And that's true to some degree on smaller scales as well, and we'll talk about that in more detail. And finally, this is, I think, really important, that we need to know our backgrounds and our imposter signals better. I think particularly for astrophysics, when we have to rely a lot more on observations, empirical evidence, and what we can learn about these other systems, I think it's really key for us to put more energy and thought into knowing these backgrounds, because by doing this, we can significantly increase the sensitivity of our searches. So I realize I'm talking to a diverse audience. I just want to point out in very broad terms what we expect for signal and background energy spectra. Stefan already showed, I think, a similar plot showing what the energy spectra of different dark matter candidates will look like. To really boil it down, dark matter tends to give bumps, lines, which would be exciting, and cutoffs. Many astrophysical sources make power laws, and they may have exponential cutoffs. And some astrophysical sources, for example, pulsars, also give bumps. So this is just a plot. I want to point out, so this is an example of a good power law in astrophysics right here. These two sort of gold lines are two different dark matter models, and this purple one down here is the energy spectrum of a millisecond pulsar. It doesn't look exactly the same, but you get the point that in certain energies, they could look very similar. So you can get bumps from things other than dark matter. I'm going to talk about a few instruments. The first is the Fermi Large Area Telescope, which we already heard a little bit about. So Fermi is in orbit. It's working beautifully. It's taken about 4 years of data so far. I want to highlight some of the key differences between the LAT and some other experiments I will mention. In particular, you want to notice that this looks beautiful. It's you might guess from this image that it has an enormous effective area, roughly the size of California, but that is misleading. You should in fact look at this panel over here, which has the requisite image of a person standing next to the instrument, and you can now see it's more like person-sized. So that is one thing that the LAT is more limited in terms of effective area, compared to the other higher energy instruments I'll talk about. In particular, CTA, as a future instrument that there's a lot of potential for dark matter searches with. This, on the other hand, does have an enormous effective area, and the effective area is increased by about 5 or 6 orders of magnitude over what the LAT achieves. So to compare the current and projected future capabilities of the LAT and CTA and some other observatories, here's a plot of the angular resolution, so 68% containment in degrees as a function of photon energy, and this is the energy resolution as a function of photon energy. So right off the bat, you see that the LAT is operating typically at lower energies than CTA. But also that CTA tends to have improved angular resolution and energy resolution at those higher energies where it reaches. So one thing we might want to be thinking in terms of future analyses is how we can fully take advantage of the enhanced energy and angular resolution, as well as the enhanced effective area of CTA. One important thing to point out for some of these searches is that the LAT is very efficient at rejecting charged particle backgrounds. It's very efficient at identifying gamma rays and not confusing them with things like electrons and positrons. That's not necessarily the case for CTA, so while there are certainly a lot of techniques that one could use to get around that or to certainly make excellent source analyses, diffuse emission, particularly large extended diffuse emission, is more challenging for IACTs like CTA. I do want to mention another gamma ray experiment that is on the horizon. This is Gamma 400. It looks a lot like Fermi. It's a little bit longer, but otherwise it's fairly similar in design in the way that it's intended to detect gamma rays. My understanding is that this project is now fully funded in its baseline configuration with a launch scheduled for 2018. There's been some interest recently, a couple papers on the archive about this, so I do want to make sure I mention the specifications of Gamma 400 in addition when we're thinking about optimizing searches. So this is a comparison of the Fermi LAT and Gamma 400 capabilities. This is actually coming from the Gamma 400 performance paper. What you'll see is that below about 10 GeV on this plot, this is again the angular resolution as a function of energy, and this is energy resolution as a function of energy, with the red line being Gamma 400 and the blue ones being Fermi LAT. So what you'll see is above 10 GeV, you can start to see an improvement in the angular resolution with Gamma 400, and above about 1 GeV or so, you'll start to see an improvement in the energy resolution of Gamma 400. So this is very exciting, and it suggests that we could start doing more precise measurements and take advantage of this capability. It is important to keep in mind, however, that Gamma 400 has a smaller effective area than the LAT, and the LAT is already about 5 to 6 orders of magnitude smaller than CTA. So the energy range where we're expecting to get this improvement is already statistics limited, so we'll have to keep in mind that even if we can measure photons' energy and angular position much more accurately, or more precisely, we're going to have to deal with limited statistics in that case. This is a comparison of these gamma ray experiments. The only reason that Gamma 400 is in bold here is that I took this from the Gamma 400 paper. If you want to extrapolate anything about the optimism of those numbers, you can do that yourself. So I do want to highlight just a couple of the features here. As I already mentioned, effective area I think is very important. Again, this is the LAT. This is Gamma 400, about half of the LAT's effective area, and then CTA is way up here at 10 to the 6. The angular resolution, to compare, this is the current energy resolution, or angular resolution we have above 100 GeV with a LAT of about 0.2 degrees. We can expect a very, very large improvement with Gamma 400 of more than an order of magnitude. However, we'll also see an improvement with respect to the LAT by going to CTA. And finally, in terms of energy resolution, we don't expect to see a large improvement between the LAT and CTA, although at high energies we might expect to see improvement with Gamma 400. So there's a lot of very interesting prospects here. I won't talk in detail about Gamma 400 after this, although I will mention some studies involving CTA future sensitivity. So in this talk, I would just like to focus on a couple search targets. There's obviously very, very many possibilities, and the issue of astrophysical signals contaminating these measurements is an important one for many, many studies. So I've chosen two that I think really demonstrate the importance of understanding these astrophysical signals, and I'm going to talk about some techniques people have proposed to get a handle on the astrophysical backgrounds. And these are also targets where I think that improvements could significantly improve our dark matter constraints. So first, the inner galaxy. These are a couple images of the high energy inner galaxy. We already have a lot of very interesting data on it. It's very interesting for astrophysical reasons, obviously. So this, on the left side here, this is a count map from Kev Abizadeh and Manoj Kapling-Hatt's recent paper showing roughly the inner 3 degrees of near the galactic center. And this is at energies of about 1 GeV using Fermi LAT data. So for comparison, here's the Hess data, measurement above 380 GeV, so at much higher energies. And for comparison also, you can see this black rectangle here corresponds to roughly the region that's shown here. So immediately you can see that it looks a bit different when you go to higher energies. For one thing, we do have much better angular resolution, so we start to see things we couldn't see with the LAT data. But there's a couple other interesting things that come out of this. One of them is that it seems from this analysis here, and also from a few other analyses, although I think there is a bit of discussion about that, that the inner galaxy appears to have a spatially extended emission. You can't model all of the emission well with a point source. I think maybe Simona and other people on the committee or the panel will talk about this afterwards. So this is interesting because, on the other hand, if you take this source here in the Hess data, sorry, this is all the data, and this is the residual after you subtract a point source, it looks like this central source here is actually very consistent with a point source. So we're seeing two different spatial extensions, or rather a spatial extension at one energy and not at another one when we start looking at different energies. I should mention also there are, in addition to this question of what is making up this emission here, you have all this diffuse emission, you can see this here. There's a lot of point sources in this region. These are something, I think there's on the order of 20 sources that were detected by the LAT, and they're all represented by these white circles. So in addition to the question of what diffuse stuff is going on there and possible dark matter, we also have sources to contend with. And down here, I just want to point out there's a lot of really nice structure that you can see. This is stuff that does not look very much like an expected dark matter signal. It may be interesting for other reasons, but it's certainly going to contribute to the total emission that we measure. Another nice thing that was pointed out recently when you combine the Fermi and the Hess data, this is from Alexander Belikov et al. That Joe showed this plot yesterday, I think. This is the spectrum. If you take the Fermi data on the Galactic Center source, this is from another paper, and the Hess Galactic Center energy spectrum. So this is E squared dNd as a function of E. See a nice power law here. We always want to fit a power law to an astrophysical source. But some interesting things were pointed out. In the Fermi data, you seem to see somewhat of an excess if you try to fit it with a power law at a few GeV. This is the same emission that some people have suggested may be related to a light WIMP candidate annihilating into, I think BB bar or taus might also be able to produce this. So you see this bump right here. But then it looks like you might be able to fit the rest of this to a power law. But then you go over, and you can extend it pretty well. And you get over to the Hess energies, and then you see there's another bump. And this is kind of weird, because you don't necessarily come up with dark matter spectra that have two bumps. And you don't usually come up with astrophysical spectra that have two bumps. So this might be another clue that the physics that's producing this emission at two different energy scales is a bit different. We do, however, have to keep in mind that we're also looking at different spatial scales. And that's something I'll talk a bit more about later. I do definitely want to point out that multi-wavelength observations, in particular of the Galactic Center, are really important. This is a map of the same region as shown here from VLA. This one's just a bit rotated, but the scale is actually very similar. And in radio, you can see all kinds of fantastic structures. The radio angular resolution is really great, and it can help map out a lot of the things that are not dark matter, as well as possible dark matter signals in the radio coming from, for example, synchrotron from high-energy electrons and things like that. So Stefan showed this plot, but I've added a couple annotations that I want to point out. So he did point out very nicely that this plot shows that there's a difference in the predicted density profiles from in the inner region of the galaxy, but it happens very, very close to the inner regions. When the regions that we're actually observing, we're not able to, there's a small difference, but maybe not quite so big. And as we heard yesterday, it's possible that none of these profiles are realistic at all, and in fact, they should all be cores. And we should be considering that. But for the moment, let's assume that we don't know what the dark matter distribution looks like in the center of the galaxy. I should point out that this is rho times r as a function of r. So that means that if w, which goes as r to the minus 1, is shown here. It's a horizontal line. So the couple scales that I pointed out, for one thing, you can see right off the bat, the radio has very good angular resolution. It can start really probing in here. But since we're not expecting prompt emission in the radio, that doesn't really help us for mapping out a dark matter signal. As you go farther out, actually, let's start out here at about 100 parsecs. This is roughly my estimate using the 68% containment. This is roughly what you get for gamma 400 or Fermi-LAT at 1 GeV. It's significantly outside the region where we see differences between the profiles, so it would not allow us to distinguish a candidate that way. As you move in a little bit, you get to the CTA or Fermi-LAT at about 100 GeV right here. You move in about an order of magnitude. And then finally, with gamma 400, in principle, you could get down to about here. Now, there's this other thing I've marked here, which is this circumnuclear ring, which is a ring that I guess has been discovered by radio observations of a whole lot of interstellar gas around the galactic center. And interstellar gas is something that is a great target material for cosmic rays to then produce gamma rays. So we do expect that there will be another component of the signal coming from the region within which the Fermi-Lat and also CTA is sensitive. So it's something we should definitely keep in mind, that spatially there are other things going on within our angular resolution element. So some nice work that was done recently by Tim Linden and Stefano Profumo was looking at whether or not we could test the hypothesis of the galactic center being a point source or not using CTA. And so what they're looking at here is this is distance. This is the cumulative counts as a function of distance from the galactic center. And they're showing this for a point source, which is this black line here, a hadronic model, which involves having high-energy protons collide with the interstellar gas, and then two dark matter profiles here. And at the roughly what you might expect to be the angular resolution limit of CTA, there are significant differences between one of the softer dark matter profiles, not so significant differences between these other possible models. However, one thing they pointed out, which is interesting, is that if you look at the azimuthal counts distribution, so if you look at the galactic center and you map out the number of counts you get as a function of azimuthal angle, if the emission is actually extended along the plane, you would not expect to have uniform counts. So in the case of a point source, you would have uniform counts if you stay a fixed distance away from the galactic center. But if there's a little bit of extension along the plane, you would pick that up. And this is a calculation for CTA with 500 hours. So they're showing that with CTA, they could more carefully probe the origin of this emission and see whether or not it's consistent with having some hadronic component. So to summarize on dark matter in the inner galaxy, dark matter is likely the brightest the inner galaxy is likely the brightest dark matter source in the gamma-ray sky, but is embedded in large and complicated backgrounds. We have resolved sources, which we can see. There are unresolved sources. Necessarily, there are fainter friends of the sources we've already resolved. And there's also diffuse emission coming from a variety of sources, and that makes this a very difficult region to study for dark matter. So to go back to the three tools I mentioned before, spectrally, the dark matter signal might be subdominant, which would make a spectral signature difficult to identify, at least if we're not able to get rid of some of the other backgrounds that are dominating the spectral features. Spatially, we could have strong spatial signatures. However, this is a source of uncertainty, particularly with the dark matter profile. But these scales are not accessible with current data. So it looks like we're going to need more data and data with higher angular resolution to be able to take advantage of this mechanism for reducing astrophysical backgrounds. And lastly, to know your backgrounds and imposter signals better, pulsars and other astrophysical sources are a major source of emission in this region. Obviously, there are people that study these things because they think they're interesting in their own right, and we can hope that with more and more data, we'll actually start to learn a lot more about these things. So for the future, I think that putting 1 and 2 together, the spectral and the spatial information, could be really key. If we use this improved angular resolution, we could help determine the morphology of the emission in the galactic center, and hopefully address differences between the GeV and the TeV results. Also, if we combine the spatial information with knowing these background signals, in particular by using multi-wavelength studies that can access smaller angular scales, these could help pin down the origin and the spatial distribution of some of the components. So for the last part of my talk, I'm going to talk about the isotropic gamma-ray background, or IGRB. Stefan showed a few plots about this already. I'm going to talk a bit more about how we can do better in the future with this. He gave a nice status update already, though. So the original question is, what is making the diffuse gamma-ray background? And a couple of years ago, this became very interesting because the Fermi-Lat released their measurement of the IGRB energy spectrum. And they showed it to be a power law. So another nice power law right here. This is E squared dNdE as a function of E. And you see this nice power law here. But the thing that was really interesting is that there was an analysis of the source count distribution. So it's the number of sources as a function of flux of the Fermi-Lat detected sources, the vast majority of which are blazars. And from extrapolating that, as Stefan said, to lower fluxes, you can come up with how much the unresolved members of the blazars are contributing to the diffuse background. So when they did that, what they found was that blazars cannot make up anywhere near 100% of the background. It was left to be unknown contributors. And the reason that this is a very simplified picture is that until a few years ago, there were certainly models that could explain all of the gamma ray background using just blazars. And there were still some models that persisted even after this measurement. So we actually have a bit more information now, so it doesn't seem like quite a stark difference. If you start adding in a couple more source classes, particularly ones that maybe we didn't have as many detected members of, you start to fill in the gaps. And you're leaving less and less room for dark matter in the IGRB. So this is the same plot that Stefan showed, so I just want to point out.
What's your definition of a blazar?
I'm sorry, a blazar is an active galactic nucleus with its jet pointed along our line of sight. So what we have here, again, this is the same data here with these extra blue points. These are preliminary measurements extending up to a few hundred GeV. We have the blazar. The blazar component is now broken into two subsets of blazars. One is BL-lax, the other is flat spectrum radio quasars. We saw the BL-lax become dominant at high energies. The flat spectrum radio quasars are more important at low energies. It's a large component filled in by radio galaxies, and then another fairly large component filled in by star-forming galaxies. These are all good, well-known sources of gamma rays. So you sum them all up, and you get this yellow band here. And if you look at the fraction of the IGRB you're accounting for, you're now getting something like 60 to 100% of the IGRB, which is an energy-dependent statement. But what's interesting about this is now we're starting to close the window. Now we're starting to edge out where we can put dark matter, if we believe this. Now we do need to keep in mind there are fairly large error bars in these models. So one of the natural things that we should improve is if we can improve modeling of these source classes, we can really get a handle on what's definitely there and what isn't, we can hope to actually start making better constraints from the isotropic gamma ray background. So there's already been attempts made to constrain dark matter from the IGRB. In particular, this is, again, the IGRB data. And these are some predicted energy spectra, E squared DND is a function of E, for different components and different assumptions for the dark matter structure. And what you should take from this plot is that there's a lot of uncertainty. There's a lot of uncertainty in these models. So that's going to make it difficult. All right, I'm going to go through this a bit faster. So Stefan already showed these constraints. They look like they're getting interesting in some cases, not in others. Obviously, they will get much better if we could start tying down what else is making the IGRB. We can also get rid of the IGRB, which is fantastic. It was pointed out by Abizajan and collaborators that the IGRB is, in fact, a time-dependent quantity, and as we resolve more and more sources, it's going to get smaller. So future IGRB measurements will naturally lead to an improved dark matter sensitivity, even if we know nothing else about what is making it up. But we can do better than just detecting more of the unresolved sources. We can model them, which is we've already seen, but we can also use other techniques and observables to identify their contribution to the IGRB. So in particular, this is one that I like personally. This is detecting unresolved sources with anisotropies. The main idea is that diffuse emission originating from one or more unresolved source populations will contain fluctuations on small angular scales due to the variations in the number density of sources in different sky directions. And then you can use the amplitude and the energy dependence of the anisotropy to reveal the presence of multiple source populations and constrain their properties. So the anisotropy is another IGRB observable. So very briefly, I showed you these maps before, and what you should take from this is there are small-scale fluctuations in the expected photon distribution coming from dark matter. This is also true of pretty much every other source population in the universe. So we would like to characterize these fluctuations and find a way to use them to separate populations. I'm going to use the angular power spectrum. I think you probably all know what that is. I'm using it in a fairly standard way. Okay, the angular power spectra of unresolved gamma ray sources, not dark matter. So it turns out that gamma rays are really boring for anisotropies because the angular power spectrum of pretty much every gamma ray source class, except for dark matter, is dominated by the Poisson or shot noise component above multipoles of about 10. That means it takes the same angular power at all multipoles. We have predictions from the literature for a number of plausible gamma ray source classes. These are some rough numbers to give you a sense of the range we're looking at. In contrast, you expect something kind of similar for dark matter. However, at large multipoles, above about 100, you would expect the dark matter to fall off faster than Poisson. So this is Poisson here, this little dashed line. You see it falling off. This is for dark matter annihilation here and decay over here. So the current measurement uncertainties are unfortunately too large to be able to identify a dark matter component via scale dependence, but it may be possible with future measurements, even with just better statistics. We already have some constraints on dark matter from anisotropy because the first measurement of small angular scale IGRB anisotropy was made recently with a Fermi lat. What we can do then is we take this measurement. This is the Poisson angular power in normalized units here as a function of energy in 4 energy bins. This is what was measured. It looks fairly flat. And what we can do is if we simply require that the anisotropy from any particular source population does not exceed the data, we can place an extremely conservative constraint. And from that, what we get for galactic dark matter is it can't make more than about 40% of the gamma ray background. And for extragalactic dark matter, it's a bit weaker constraint. But we would imagine that we could do quite a bit better. In particular, we know that things like blazars produce a lot of anisotropy and are likely to be producing some significant fraction of the IGRB. So we can start in the same way that we would chip away at the intensity from different source classes that are part of the IGRB. And again, if we can constrain that better, we would hope that we'll be able to narrow the window for how much dark matter could be there. We can also do the same thing for anisotropy. If we start filling in what other source classes are making that anisotropy, we leave less and less room for dark matter. So in my last minute or two, I am going to talk about a new technique, which I think will be very interesting. This is some preliminary work I've been doing. It should be on the archive in a couple weeks. This is work with Brendan Hensley at Princeton and Vasiliki Pavlidou at University of Crete. So the idea here is to make some fairly simple assumptions about what is going into the gamma ray background. Simple, but in many cases very realistic assumptions. And use very simple algebraic techniques to separate the components. And the key thing here is we have to observe an energy-dependent feature in the anisotropy. So we need to see the anisotropy changing with energy. And under these simple assumptions, what that's going to allow us to do that I think is exciting is to extract the energy spectrum of each component without assuming the shape of the spectrum or assuming its anisotropy a priori. So in particular, I'm going to make 3 assumptions I need to point out. I'm going to assume the IGRB is primarily made by 2 components. There are some cases where I can deal with 3 components, and if I can model something out and get it down to a 2 or 3 component scenario, I can handle that as well. I assume the components are uncorrelated. This is a very, very good assumption for gamma ray sources. I'm going to assume that one component dominates the anisotropy at low energies. This is also a fairly reasonable assumption. For example, something like blazars at low energies might be dominating. So I'm only going to need these equations here. I'm going to relate the observables, the total intensity as a function of energy, to it's just simply the sum of my 2 components. And the measured angular power as a function of energy is simply going to be the sum of the 2 components. There are no cross terms because I've assumed that the sources are uncorrelated. So I can divide these 2 out to make another quasi-observable, which is the angular power in intensity units. So I've normalized out the intensity units. This is something that would be energy independent if I only had one source class. And that's because I'm assuming that all of my source classes, or all the members of my source class have the same energy spectrum. This is also a fairly reasonable assumption, at least over some energy ranges for most gamma ray source classes. So what we've done is we've identified several features in the energy-dependent anisotropy that can tell you something else about what's happening there. I'm going to show you one example of this. So I've highlighted it here. This is for a high anisotropy plateau. And so the observational feature is that you observe an anisotropy energy spectrum that falls from a high anisotropy plateau starting at low energies. And what this tells you is that the source that is subdominant in the intensity is much less anisotropic than the dominant source. There's a bunch of negatives in there. It'll take a minute to process, but I'll show you the example. And what's cool about this is you can pull out the intensity normalization as well as the spectral shape. You can't pull out the fluctuation angular power from this, but I think this is the quantity most people are interested in. OK, so here's your example. This is an example of observations. So in this plot, can you guys? Yeah, you can see it. OK. So in this plot, what we have in the top is an example. Oh, I should point out, I'm not saying this is the composition of the IGRB. This is an example that is consistent with current measurements that I'm going to decompose for you to illustrate a technique. OK. So the idea is I measured this intensity spectrum here. Overlaid in red are the Fermi-Lat IGRB measurement points. So I'm showing you that my future observations, assuming 10 years, are consistent with the current measurement. Although this in principle might go down, of course, but I can't project that far. This is the anisotropy energy spectrum for the fluctuation angular power. This is the plateau I'm talking about. I see something that's flat up here, and then it starts to fall off. So this is the observational feature I'm using. And just to show that we're consistent, these are the points we have that are the intensity angular power compared with the already existing Fermi lat measurement. Preliminary refers to the model work. All of the data points are already published. OK, so using algebraic techniques, this is my last slide, we decompose the energy spectra without making these other assumptions. So I'm showing the points that we get out of this model. And you see something that looks like it could be dark matter. I've drawn the lines from the model through it. And we've done this without having to assume a dark matter model or spectrum beforehand. So we're very excited about these. So to sum up with the IGRB, spectrally, the dark matter signal must be subdominant since we don't see a signature in the IGRB energy spectrum. Spatially, they're mostly isotropic, but we could use small-scale features. And it would be great to know the background, the astrophysical sources, so we could know our backgrounds and imposture signals better. And finally, if we combine the spectral and the spatial information, we could allow contributions from multiple components to be disentangled. So in summary, this is a really exciting time. There's already really exciting results, and we're already seeing hints of a detection. We can optimize our search strategies for different dark matter models, targets, and instruments. We should always think about complementarity. We could look forward to improved angular resolution of future gamma-ray instruments. And this is also would help us map out spatial signatures of a dark matter signal. And finally, combining spectral and spatial features can improve the sensitivity to subdominant signals. OK, thank you.